how large the axial contribution is to the rate and whether we have to worry about it. So this was just a way to sort of just start again, start fresh, and have a look. So I'll go through the whole calculation and finish with some of the analyses we've done. But you guys all know these since you're on the papers. And if there's time, I can talk about my code, or if anyone's interested, we can show you my code. Okay, so just the outlook. Yeah, the road to BSM is paved with dead excesses. So there's many times that we just didn't fully understand the standard model. So before we rush into this, it would be good to know if we were just missing something from the standard model. So, you know, the things we might be interested in are going to be smaller than the standard model, maybe a tenth or 100th is small. So also this is sort of a question of like how precise do we need things to be if we want to be able to detect new physics that's sort of parts per 100 level. So starting with the cross section. It'd be nice to have like a single consistent formalism where we can calculate rates, well, just the cross section across all different isotopes. So accounting for different spin effects. And the commonly used form, I put the citation in Bronco. I don't know who originally wrote it in this form, but a lot of people cite Bronco for this form. And that's valid for point particles. And you can throw in a form factor and you'll get, it turns out you'll get a very good answer. But I want to be able to consistently extend this to include effects on the fact that the nucleus is not a point. So the right formalism to do that is semi-leptonic electrolytic. That's developed by Kolechka back in '75. It was extended by Dunley and Peche, and Haxton did a lot of work on actually evaluating functions that are in this. So I make a lot of use of their work, especially Kolechka's textbook is really useful if anyone's interested in going further into this. Right. So yeah, the next sort of 10 to 15 slides are going to be pretty formal, so please ask questions if you're confused. I went through all this in a bit of detail, so yeah, just feel free to stop me if you want any more detail. Okay, so back to the fundamentals right at the start. Effective neutral current interaction for neutrino with a hadron is going to look like this. And this is, we've already integrated out the Z, but we're definitely considering the case where we're in the low energy regime. We're going to want leptonic hadronic currents. So we're going to couple the leptonic current to a hadronic current like this. And what would be nice is if we could just express this in terms of nucleon currents. The nucleus is obviously made up of nucleons, but if you ask some nuclear theorists, that's not necessarily the best basis to work in, but it is a sort of a convenient and sort of conceptually good basis to work in. So we'll do that. So first we're going to write down the hadronic currents in terms of the quark currents, and that's done here. The vector and the axial piece. So in the standard model you have this B minus A structure. So our actual current is vector current subtracting the axial current. And the goal of doing this all is eventually, since we don't think that there's going to be enough of a momentum transfer with the nucleons themselves that you'll have to worry about nucleon form factors, all I'm going to end up doing is this is just going through to derive what the essentially the long wavelength form of these are. So when you do that, we take this q squared goes to 0 limit. The vector form factor is just this is of the nucleon, will just be the vector charge, and then the axial is the axial charge. So these factors in the SEVNS literature is sort of hard to find. People don't generally talk about it, but if you're looking at higher energy neutrino scattering, and look up these formulae. Sometimes it's ignored the fact that there's some strangeness. It's been some strangeness in the proton and the neutron. So often I'll just take GA. This is called the passive scalar axial coupling. So it's been shown recently that there is an appreciable strangeness. So you do have a bit of either spin violating in the axial sector as well. So, forgetting all of that, now we can come back and write down an effective nucleon current in the low Q limit. So we're still in the B minus A structure, but now with nucleons. And all that stuff we did was just to get the values of these. So the normal vector piece is just a sum over the quarks. But the axial piece, it actually ends up summing over the spin content of the nucleons. And so those numbers come out like this. And this is included some radiative corrections. So that's why it's not quite a half. And the proton piece gets the 2 sine squared theta, so it ends up being very close to 0 for the vector piece. On the other hand, the axial charge is the larger for the proton. Okay, so the full hadronic matrix element we're going to take as a sum over all of the nucleons. This is just pretending we have just a ball of point nucleons inside the nucleus. And then, as long as Q is much less than Mn, so Mn, mass of the nucleons, not nucleus, is a GeV. So in any sevens experiment, we're not going to be talking about transferring a GeV to the nucleus. So we're pretty safe to take that limit, and then we can just expand this current in the temporal and spatial piece, and then it basically breaks down along the vector and axial lines. So that's nice. The axial piece, sort of historically, this is just how you got to it, was just the piece that coupled spin. And this was just the bit that coupled charge, overall charge. Okay, so now looking just at the neutrino part of the current, just write it with a little ingoing wave, and what we're going to do is to be able to evaluate this thing, so just expand it. We just have 2 pieces to our matrix element now. We're going to perform a spherical decomposition and then a multiple expansion to be able to evaluate this. So what do we do to do the spherical decomposition? Well, the scalar piece is easier, but for the vector piece, we have to use these identities. And so we're going to break this down into 2 pieces. One, which is the z direction, which we'll call the imparted momentum, and then these spherical vectors, the 2 spherical vectors around that axis, defined by momentum transfer. Okay, so then performing the multipole expansion, we will define these 2 tensor operators. They're irreducible tensor operators. So that has the nice property that now we can apply the Wigner-HEPEC theorem derivative to it. So our matrix element now just looks exactly like this. So we're able to reduce it in the M's. So now we just have to sum over J's. And this, since this is an expansion, we're just summing over J greater than 0, Jn, everything J greater than or equal to 0. And so then, just still keeping track, this M piece is called the charge piece, and so it's just that J0 part of the current. So it was, again, just the vector piece, vector charge. And this is basically carrying the spin and the axial piece. Right. I don't know if this is too fast, maybe too much detail, but if you're just interested in a picture of how this works. Right, so then summing and averaging those, we can write down, this line is taken directly from Kolechka, a formula for the cross-section based on these two irreducible tensor operators. And once you evaluate these lepton tensors at the front, it starts to look in a much more familiar form. So if we just look at that top line, that should be very familiar. If you just think of this squint and then think of this as a form factor, then you're pretty much there. But yeah, so now we have this extra contribution which comes from the axial piece. Okay, so I don't know who this parlance is due to, but these get called nuclear responses in the dark matter literature. That's what I'm calling them. And we will define them in first quantization as just the sum over all of the nucleons in each nucleus of these individual single particle operators. So it's sort of a backwards definition. We're going to define this, and then from this definition we will identify what this operator is. And that's using the original definition of what these irreducible tensor operators, you define these single particle operators. Now if you look at the transformation properties of these, the M, since it's just a charge, it just transforms under parity and charge parity as even. But the vector axial piece is an axial vector, so it's odd under parity. The consequence of that is just that I've already taken it into account here. Only the even multipoles contribute here, and only the odd multipoles contribute here. And what that actually serves to do is that we already used the fact, writing down the previous formula, is that there's no, since they contribute on odd and even separately, there's no interference effect between the axial piece and the vector piece, which actually people have done that in literature. So that, at least at this order, it's not the right way to do it. Okay. Oh yeah, so just to point out, and then in the long wavelength limit on this, so you just taking Q to 0, this is just proportional to 1. So you can just think of this as just counting up all the nucleons and assigning it a charge of either if it's a neutron or a proton. So that's all that does. This one, this is just going to be, it just turns into sigma, it's the Pauli spin matrix, so all it's doing is, in the long wavelength limit, this becomes just, it acts on the spin of each nucleon. So it just counts up the total spin of the nucleus. And then it comes along with the axial charge.
So yeah, so
yes. Okay. So how do you calculate these nuclear responses? Well, I haven't actually done it by hand, but Paxton years ago churned through and did a bunch of these, and now it's written codes to do the rest. So if you have the density matrix, at least if you're interested in coherent scattering, elastic scattering, then you want just ground state to ground state transitions. And then these matrix elements, if you have to choose a basis to evaluate in, so they tend to work in the harmonic oscillator basis, because that way you can just get an analytic expression for the matrix elements. So if you've ever looked into some of these form factors, they always carry these factors. This is just a bit of a side note, just to say that this gets done in a computer and you get a nice analytical formula out of it. But yeah, you do have some model dependence by the fact that you've chosen to model the nucleus as a harmonic oscillator. Okay, so the form factors now, to make this look more familiar, if we define the form factor as this response function summing over all of the multipoles, and then this factor just cleans up the rest. And so we'll define one for the vector piece and the axial piece. And then you're able to write down the cross-section like this. So now it should look very familiar. If if you just factor out, if you pretend that your neutron and proton form factors are the same, you can basically just factor this out, and it will look like. So the way this form factor is defined, this will be normalized to the number of neutrons, and the proton one is the number of protons squared. So this is exactly, at least for the vector piece, is exactly the result you get in the first equation I showed. In the case of the spin piece, though, it's not quite the same. So I will show in a few slides. I'll do a comparison with these. But I wanted to just include this little physical picture of what the form factor is doing. This is just a reference that came last year. It was presented at this Magnificent Sevens workshop. We talked about this a little bit. I thought it was an interesting way to view it. So if you think about what we're doing, you have, this goes for dark matter as well, or for the dark matter scattering, or the neutrino coming in and imparting some momentum. And we like to talk about it scattering with the whole nucleus, but really it's just hitting an individual nucleon in the nucleus. But we want to sum over all of the effects of all of the nucleons. So how is it that you can scatter from a nucleon and impart some momentum to it, but at the same time scatter from the whole nucleus? Because you have to transfer the same amount of momentum to both the nucleon and the nucleus. But you can't transfer the same amount of energy, kinetic energy, to each. That means that, like, as a whole, we know that kinetic energy has to be conserved. Or total energy has to be conserved. So that would mean that you can't conserve it at the individual level. So it's sort of a bit of a paradox. Like, what's going on? How do you not conserve it at the level of the nucleon, but conserve it at the level of the nucleus? And the way to sort of think about it is that all of these nucleons are bouncing around inside. So they have initial momentum. So if you write down now an equation for momentum transfer, including the initial momentum, then you come up with a condition, and there is a unique momentum of an initial velocity of a nucleon inside the nucleus that can conserve momentum and energy at the vertex. But you might think that, okay, what's the chances that a nucleon inside has the right incoming momentum to do all the conservation and know about what's happening on the large scale? And really, so this is what the form factors do. It's the fact that the form factor is integrated over the wave functions for all the individual nucleons inside. And that, so all the nucleons are not sitting there in eigenstates of momentum and energy. Yeah, they're smoothed out. So basically, there's an overlap. For lower momenta, you have sort of more leeway. You have more incoming momentum, then there's less of a chance that you're going to have the right incoming momentum for the incoming nucleon inside the nucleus. So the higher the momentum goes, the form factor goes down. Basically, it's not able to sum over as much of the tails of these wave functions of the individual nucleons. Sort of makes sense, the picture I'm trying to draw. This paper explains it much better, so it's just kind of reading it. Okay, so just analytically going through and getting those form factors out, and with so MP stands for the multipole expansion, and plotting them and comparing it to the Helm form factor, which is the ones that we mostly use in literature, but also to a two-parameter fit to the charge distribution. So this is for germanium. So if you get the charge distribution, it's like electric charge distribution. You can just Fourier transform it, and you'll have a form factor, and then normalize it. So what you see straight away is that it's pretty much the same. And if you integrate this thing, and also I've had to plot out to 200 keV energy transfer just to see a small difference. So the discrepancy in the region that we're interested in, way down here, is less than 1%. So basically, it seems like, at least for sevens, when you're doing momentum transfer, it doesn't matter which parameterization you use. You get a very similar answer. It ends up, we'll see at the end how many events it ends up affecting, because I'll propagate it When we look at the axial case, well, we can't do these other form factors. So this is just the multipole expansion. And the three different lines here are just the proton, proton, neutron, neutron, and then the interference term between them has its own form factor. Yeah, so straight away you'll see that they're pretty small, unless this is the neutron-neutron one. You have an unpaired neutron. So this is for germanium-73. If you look at germanium-74, it has none of these. They're all zero, because there's no unpaired neutron or no unpaired proton. So basically the machinery behind this is all going through, it's summing over all of the individual spins inside the nucleus, and if they all add up to zero, there's no form factor there. Now in reality, there's probably a higher order effect, but this is already small, as we'll see, so the fact that there's a higher order one means we can ignore it completely. Right, is there anything else to say? Oh yeah, so then we're hurt by the fact that this is, it's germanium-73 is only 8% of naturally occurring germanium. So we're not very sensitive already to the spin, and then you have to divide that by a factor of 10. Yeah, so we'll see that when we get to rates later on. I just did another one for iodine, because so you probably know the coherent experiment. Used cesium iodide for their first sort of detection of sevens, and they both cesium and iodine have unpaired protons. So they have a bit of spin in the proton-proton form factor, and then since they're larger nuclei, you do actually start to see a larger discrepancy between the multipole expansion and the Hell. So the lower energy. Larger nuclei, they lose coherence more quickly.
What's your aggregate binding? So you have neutron, neutron, proton, proton.
Yeah, so this one's proton, proton, then this is neutron, proton, and then neutron, neutron. Yeah. So basically this is almost zero because there's no unpaired thing, and then the interference term just gets dragged up because it's interfering with the top one. Yes, the discrepancy is now about 1%. Now, I'm not sure where this came from. I haven't talked to them, so I'll probably email Kate or Grayson and ask this, but they use 5%. They just threw out 5% as their uncertainty in the form factor. Now, it probably doesn't matter because their uncertainty, they say, is dominated by their quenching factor, which is like 25%. The total uncertainty they had was 28%. So this contributes maybe a little bit, but flux also contributes. So it's probably not a big deal that they chose such a large number. I just wonder why they chose 5%. Yeah, and so again, this is over the region of interest. So for coherent, you also have to integrate over a larger energy range. So the one for germanium, I just integrated over where we're interested in, which is up to 2 keV. For them, they're interested in up to sort of 24 keV. So there's more room for discrepancy to build up. All right. Yeah. So now, just to go back and show you, this was the form of the cross-section that I derived. This is the form that we had used in past work. And this is the Bronco form, but rearranged to just keep up to ER over E nu. So basically, the interference terms drop out of their formula. So just looking at the vector term first, these are obviously exactly the same. And once you factor out a common form factor, you'll get exactly the same answer. So these are all consistent. The only thing you lose is the fact that your neutron form factor is not exactly the same as the proton form factor. But as we already said, that's a small discrepancy. But it is something to maybe keep an eye on. That it might be at the 0.5% level. So it's worth keeping track of separate neutrons and protons. But now looking at the axial pieces, this formula that we used previously was motivated by how it's written down in the dark matter literature. Now, depending on how you normalize different things, this could be correct, but I don't think it was correct as we used it at the time. Yeah, so if you just factor out GA from these, you get something that looks more like this. But what they've done here by just writing, so their sum over spins, they write as Z plus Z minus, whatever that means. You can't really look up, and it's not even consistent, what is, how many spin up and spin down protons and neutrons there are. So I think they just wrote it like this, acknowledging that this is, you have to do something like this. But to actually do it, you've got to sum over the wave functions properly. Yeah. So, and then actually, interestingly, there was a factor of a half different, but not without knowing how they define the axial form charges, it could be consistent. But yeah, if you take it at face value and plot them, this is the difference you get. So our old form is in orange, the Bronco form is up here, and my current calculation is in blue. So it's smaller and it drops with energy because now we're including the form factor. Yeah. And so this is plotted, for whatever reason I chose to do it at 30 MeV.
So what's the vector in those units?
Yeah.
Like,
Pardon?
what's the vector scale of those units?
The vector scale like this.
Yeah, in those dimensions.
We're in G.
Like, so it's -4, -5 or something. Or what's the, so that's the axial cross section, right?
Yeah, it's the axial piece of the total cross section.
Yeah, that's right. So what's the vector piece?
On this.
It's like above
right.
the ceiling, or like, yeah, that's
Did I plot it? Yeah. I think it's about 100 times bigger.
okay, that's what I'm. Is it, okay, more or less, like, constantly shifted overall energy?
No.
Why is that?
It's not shifted over on.
Why is it 100? It should be much bigger because coordinates.
Well, this is the axial piece. This
Oh.
is the contribution of the axial piece.
Sorry,
So if you go back to your previous cross-section form.
Compared to the vector, I see.
Yes, yes.
Yeah. Yeah, I think I plotted it across the top. So this is now just plotting the axial cross sections for different nuclei that have spin. So germanium-73 is in blue, sodium has a nice big spin, it's in orange, iodine's green, and then fluorine has the largest spin, it's in red.
So you're saying this could be like, if you bring a pico detector
Yeah.
with the SNS, that'll do the best job in understanding for.
Basically, yeah, so since it seems to gain with energy, you want something that is light, so fluorine does better. Because what I haven't plotted on here is each of these will have their individual endpoint for the spectrum. Fluorine being light, it's a better kinematic match, so it can have a higher recoil energy. And so here I integrated over, this shows it better because I integrated over this from 0 up to the endpoint. This is the total cross section as a function now of the neutrino incoming energy. Yeah, so germanium actually ends up winning on this scale, interestingly. But yeah, again, if you have just natural germanium, you only get 8% of the cross section, where fluorine has one stable isotope. So if you scale it by that, we'll end up pretty similar. Yeah.
So does silicon lie on this?
I did not do silicon. I'll add it before I.
That is like 5% unpaired spin.
Yeah. Okay. So now, since we're talking about small effects, you should ask at this point, well, what about the neutrino charge radius? So yeah, you get a small correction to the cross-section due to the fact that the neutrino interacting just as proton coupled neutrons has an electromagnetic vertex correction. So that comes in and just affects the vector. It doesn't affect the axial piece. And when you calculate this thing, it's about 0.02. So remember, this charge was actually about 0.02. So for the proton piece, it's affecting it at order unity. But you got to remember that we normally talk about scaling as the number of neutrons squared. And then actually, interestingly, there's a second piece which doesn't add coherently, because what it accounts for is actually the chance that you'll flip the flavor of the neutrino, which are in a sort of coherent elastic event. It's not strictly elastic, but it's very, very nearly elastic, since the neutrino flavors are all the same. I didn't include that in this plot. If I'm just doing just the first piece. So what you see is that it affects it, but only in a very sort of small level. And here's a plot to make it clearer. This is the correction to the cross section. So I just subtracted it off. We're talking on a value that is a value that's a few by 10 to the 6. The correction is about 5 by 10 to the minus 8, so about 1/20th. But then it drops very quickly. And for the axial piece, the contribution is more like 10 to the minus, a few by 10 to the minus 10, but it's consistent across energy. Yeah, so anyway, the end point of this discussion is just to say that you should worry about neutrino charge radius before you worry about the axial piece. Yeah. But they're both things to consider. Okay. So now, before we talk about rates, let's have a quick discussion about fluxes. So the reactor flux, that's sort of something that I just reminded myself of. We normally talk about the fact that, oh, with coherent scattering we don't have a threshold. That's nice, because 72% of the flux is below the inverse beta decay threshold, which is the common channel that we use to detect reactor neutrinos. But actually, germanium with a threshold of 100 eV doesn't do much better. So its threshold is the blue line. Actually, it doesn't do better, it's worse. At 100 eV nuclear recoil, you're slightly above the inverse beta decay threshold. So you're only getting 27% of the flux. With silicon, since you have that better kinematic matching, you do a bit better, you get 44% of the flux. And then if you're able to reduce it to 70 eV nuclear recoil, then obviously these come down and you tend to read a bit more. But you're still missing this. But also potentially what's good about that is that the claimed uncertainty of this is normally a few percent. There are all these sort of reactor anomalies. So the general trend has been that measurements of reactor neutrino fluxes have shown that it's a bit lower than the Huber-Muller model. But actually, so this other model, which I don't know much about, this Vogel model, it's sort of bang on with that. So, I don't know.
Is that just like a fitting function?
The Vogel.
There's some that's like,
I don't know
think
much
it's just
about
literally
it.
a fitting function.
Whatever it does, whatever they use to get it, it fits it.
That might be why it works.
Just because it fits it. I'll read more about it.
Yeah.
But yeah, so the fact that we claim there's a few percent, you may want to bump it up. You may want to talk about it in more than 5% to be conservative for now. But yeah, eventually it would be good to nail this down. So, they claim a very low uncertainty in this diabase paper for the overall flux. So it does bring it to a few percent. I don't know what to make of the fact that these are all at different distances, different probably detection modes. So doing just a big world average, I don't know if that's the best way to talk about it. Anyway, it'd be nice to have a model which consistently predicts it. So I'll look more into the Vogel model. For SNS, they obviously have their 3 separate component fluxes, and there's Michel spectra. So when you put your thresholds on here, even though they had 4.2 keV threshold, you capture most of the flux. So, and if you had 100 EV nuclear recoil germanium there, you basically capture everything. Everything would be above threshold. So that's a good bonus from the higher energy neutrinos. Even though you start to lose a little bit from the form factor, you gain a lot in flux. They claim their uncertainty is 10%. They do Monte Carlos on this. They think they've improved them. I won't argue with that. Apparently, though, there's a bit of some of the uncertainty is just in the pion production rate. And since their beam changes energy, the target heats up, there's a lot of different effects that go on. So 10% maybe is about right. It is nice that we wouldn't have to deal with that. We have a much more stable flux. Okay, so coming into the last section. Louis, maybe this is what you're interested in seeing. So this is like the full vector rate after you've included everything at coherent, and then compared to the axial contribution to it. So yeah, it's really small. If you integrate it, the Helm is 182 events, the multiple expansion 177, axial contribution is 0.01. It's tiny. So yeah, and the neutrino charge radius being like about 20 times this is about 0.2-ish. And that is reflected if you go back to that paper that I sent about the neutrino charge radius. They can only set an upper limit on what is the charge radius, being about a factor of 5. So a standalone value. Yeah, so coherent expected 174 in their calculations. I've never actually been able to sit down and exactly get out their exact numbers, but we're pretty close. And the observed rate was 134. So obviously this, if you've seen the paper, they say they got 77% of the standard model, but they don't claim that this is some big measurement because they have such a big uncertainty. It's within a couple of sigma.
I think you might know the answer, or you might have said, like, did that expected, what form factor is that, goes into that expected 174?
In theirs?
Yeah.
They use the Helm.
Just the, okay.
Yeah.
So you're predicting and once again, how does your 182 different than what they?
Well, it's
So there's no
I don't know
that's
where we differ exactly.
Yeah.
I've used a sort of, it might be in the quenching.
Yeah, but this is a little bit of just an academic.
Yeah. It was
just
to me, it was like, oh, it's close enough.
Yeah,
I didn't have
yeah.
the numbers they
It's
used.
absolutely close enough. Just curious to see what that.
But it would be nice to get
Yeah.
closer. Yeah. Yeah. All right. So it kind of surprised me though that even though this looked like it was just a 0.1 sort of difference on the level, 0.1% difference on the level of cross section, it does actually give you 5 more events. So Helm gives you 5 more events. So that does start to look significant. And I don't know, and there's no good way to evaluate what is the uncertainty on the multiple expansion. The Helm form factor, you can play around with the inputs to it and vary it, but yeah, so that's sort of something in future work is to work out what is a good level of uncertainty to do for these. Okay, so for doing the same thing for minor, I should put in inverted commas, I would run 1 per 100 kilogram days, taking a threshold of 100 EV. The Helm form factor you expect 240, and the multiple expansion 239. So since you're not probing the form factor as much, you're pretty much straight on. You do get a higher contribution to the axial rate, but we're still talking very small. So you potentially need tens of thousands of kilogram days before you could start to get events that you would attribute to the axial contribution. And then if you could even contemplate digging that out of the uncertainties, I don't know. So I don't think it's something you could, in principle, even measure a long time down the road. But yeah, at least this is something to say, but we don't have to worry about it. So at least your new physics searches that are in this regime, tenths and hundreds of the standard model rate, you don't have to worry about the axial contribution. On the flip side though, you can use this formalism if you have a new physics contribution that is an axial vector, then this is the correct way to calculate it. So there's that. Okay, so the last few slides, I'll just step through the different sort of statistical tests that I've applied, and I've written code for all of these, so this is sort of advertising the code. And if anyone wants to learn to use it, just come and speak to me after. Right, so I've implemented some of the basic statistics from this paper, sometimes called the CCGB paper, Statistics Bible. They do a lot of statistics that they've used at the LHC, so it's a really useful paper to follow. A lot of useful formulae. So this basic test statistic is a log likelihood ratio, and you maximize, it's sort of a very pessimistic statistic, because you maximize over all of your uncertainties in the denominator and take the best fit and divide by that. So this is called profiling. Yeah, it gives you sort of a more pessimistic limit on what your significance you should expect. So basically, you have this test statistic will be distributed in a certain way, and we're trying to test a null hypothesis here. So if you put in a background only, and then we try and discover, say, the standard model, you can calculate a p-value based on that, and then make plots like this. So the code puts out plots like this. It does all the stuff on the right side for you. And it includes flux uncertainties. You can put in any other uncertainties you want. This just compares germanium, silicon, and cesium iodide. And actually, if you have a look, if you get the number of kilogram days that Coherent had and put it up, you basically get in the ballpark of the 5 sigma results. Even with not having the details of the experiment, this does a reasonable job at capturing what's going on. Right, so in the future, if we want to actually start narrowing down and constraining what is the ratio of the measured cross-section and the standard model cross-section, we use this test statistic. So the other one's one-sided. It just looks for fluctuations, those upper limits. And this one's double-sided. So we constrain above and below. And this is just an example, again, using germanium across different, so taking germanium green as the SNS. Red I was doing it if you had like solar. So I've implemented different sources. You can have the sun as a source of neutrinos, SNS or a reactor. Yeah, and basically if you go to the far future and have a look at what is the uncertainty there, it is basically, if you can add up your uncertainties and see that you just, in quadrature, you'll get back the right answer. Yeah. So you can do the sort of basic analysis and get there, but this gives you sort of a lot of leeway to play with the different numbers and combine different uncertainties, change the number of bins, just explore what is affecting the uncertainties the most.
Helps you understand when additional time is not useful.
Yeah, right. Yeah, so you can also just straight within this plot, you can see if you have 100 GeV, 100 EV threshold at Texas A&M reactor, then after 1,000 kilogram days, you're sort of running into systematics. So that's a useful thing to do. So then the other thing I've implemented in the code is Bayesian inference. This is just a one-slide summary. It's not meant to be a full summary, but if you haven't seen it before, this is Bayes' theorem. So it takes a likelihood, a set of prior probabilities, and this is known as the evidence. It just normalizes it and produces a posterior probability distribution. So when you talk about the frequentist likelihoods, you're never actually talking about probabilities of particular parameters you measure. You're really talking about the probability that having you assume something that you actually observe something. And so you get into these ideas of coverage that you want a certain number of equivalent experiments to be done. If you have a 90% confidence interval, then they would set limits that enclose the true value 90% of the time. So it's a bit of a different statement than saying, I have these parameters, what's the probability distribution of the parameters based on some data. And the nice thing is the way that if you do have prior information, you have a different experiment, you can plug it in, plug in a new likelihood, and this is sort of an iterative process that your posterior becomes your new product for the next experiment. So it's a really good way to include lots of experiments. So this is just an example. I took HEPEC, their recent data, generated this plot. This is just in an NSI space, two different NSI parameters. So this is from one of our papers. And yeah, so this is just saying the parameter values that I scanned over. So all of this is implemented in the code. You can just choose which parameters you set. Set up the different experiments that you want to add, and it will add them all together. So for the following slide, it adds these 4 different detectors, so 4 separate experiments, and will give you contours out in your chosen parameter space. So in this case, we have 3 different parameters, and yes, you need this many plots, 5, 6 plots to be able to see it down every axis. Okay, so I'll conclude there. So the multipole expansion is useful to get a consistent way of calculating cross sections. However, as we found out, the axial rates are very small, so we don't really need to include them. But they might be an interesting thing to use if you have new physics, or we're trying to get a handle on the uncertainties from the form factors. So we assume at the moment the errors in the form factors are about a few percent. So the thing that is sort of what we want to keep mind of is a lot of our other uncertainties are just normalization based, and these will be as a function of energy. So if we're searching for new physics signals that change with energy, then that's something we sort of want a good handle on. Yeah, so maybe we should take a more conservative error on the reactor flux. That's a good question. And yeah, so I built tools to do all these calculations. If anyone's interested, see me, or you can look at my GitHub to see the code. I haven't got the full multipole code up on GitHub yet. I'm still polishing it up, but yeah, it'll be up soon. Thanks.